So I think what we're going to do here is we have 45 minutes to talk. I want to spend a good hour talking about E. So I'm just going to kind of not have time to spend as much time as I'd like to on all this stuff. We'll just see how we do. But we're not going to do it all because otherwise you won't understand. It'll be too fast. Let's talk a little bit about energy and disturbances. That's the first thing. I do want to make sure we talk about this. Main thing, although the time average of a disturbance field may be 0, they still contain non-zero energy density, and they still are propagating net power. Just like the lights in this room, there's net power propagated by alternating current because there's an appropriate phasing between the current and the voltage. You know, if they have some phase, if they're in phase with each other, there's net electrical power carried. In the same way, when you have disturbances in sound waves or vortical disturbances or entropy disturbances, they can propagate time average energy into your domain or outside of the domain. When they propagate energy out of your domain, that starts to look like damping. They also contain time averaged energy. So a simple example would be the kinetic energy is if you had just a purely fluctuating flow, you can see that if U1 and U1 were both time varying, that the time average of this quantity would be non-zero. So I want to take a look at a little bit what these energy density and flux terms look like. So we can write a very generic energy equation in this form, where we have the time rate of change of the energy per unit volume plus the divergence of a flux vector is equal to a source term. Okay, so this would be a partial differential equation. I can integrate this over a volume, and I can write it in. And what this would say then would be the time rate of change of energy, whatever I'm measuring energy as, plus the flux across my surfaces is equal to the net source. So let's take a look at what these look like for acoustic fields. And I want to, in particular, I want to give you a feel for what acoustic energy, flux, and what source terms look like for sound waves. So I pulled this equation out of a hat, so you'll just have to take my word for it. But you can write, if you take the conservation equations for acoustic disturbances, you can actually write an energy equation for the acoustic field itself. And it turns out to look something like this. All right, and this equation is written subject to these assumptions. So what this tells you is, first of all, the energy per unit volume is given by this expression right here. And so you can recognize this as that acoustic waves, there's energy density associated with kinetic energy, and this is energy density associated with internal energy. This is kind of like, you know, or you can think of it as potential energy, that the volume of the fluid is expanding and contracting, which has energy density. This is the flux term. What this shows you that acoustic waves propagate power proportional to the instantaneous product. Excuse me. The instantaneous power is the product of the pressure and the velocity. The intensity is a vector. Flux is a vector, right? You're propagating energy in some direction, and so that vector, the direction, is in the direction of the flow disturbance multiplied by the pressure. And finally, this says that the source term is, you know, there's some time average stuff here, but what this shows you is that the source term is equal to the product of the fluctuating pressure and the heat release. Q, I didn't define this for you before, but Q denotes the heat release. All right, so let's talk a little bit about what happens when you have the time average of the product of two fluctuating quantities. So just as an example, let's say you take sine omega t and sine omega t plus some phase shift, all right? And let's take the time average of that. All right, so now this quantity instantaneously will have a component that oscillates at 2 times the frequency, right? Like sine omega t squared. If theta was 0, this would be sine squared omega t, which, if you remember your trig identities, is 1/2 plus 1/2 cosine 2 omega t. So there's a part that oscillates at 2 times the frequency, and then there's a DC shift. And so the time average equals 1/2 times cosine theta. And so for what I'm plotting over here is this time average. I'm plotting a 1/2 cosine theta here. So this is theta. This is the phase shift between the two disturbances. And so if the two disturbances are exactly in phase, if theta is close to 0, then that time average is a half, which is this point right here. If those two disturbances are 90 degrees shifted, so if you have two fluctuating disturbances which have a 90-degree shift, the time average is 0. Okay? So there's instantaneous, their product has an instantaneous value, but the time average is 0. So in other words, what you can see is happening here is that during this part of the cycle, they're both positive, whereas for this part, for this part of the cycle, they're both positive, whereas this part of the cycle, this one's negative while this one's positive. And so you work out the math, you get a 90-degree phase shift, you get 0. If the phase shift lies between 90 and 270 degrees, the product of two fluctuating quantities, the time average is negative. All right? That would be down here. So this just gives you a feel for the importance of phase, of fluctuating quantities in terms of time averages. So in particular, what I want to talk about is this source term right here, because I want to talk about how flames pump energy into the acoustic field. All right? And so what you can now appreciate from the expression that I just showed you before is that there will be the flame, unsteady heat release will add time averaged energy to the acoustic field if the product of the pressure and the heat release if it has some non-zero time average. And so what you can see is that if the phase between the pressure and heat release lies between minus 90 and plus 90, the product has a time average greater than 0. So if the pressure and heat release are exactly in phase, the flame's pumping energy into the acoustic field. If they're minus 45 or plus 45, it's pumping energy into the acoustic field. If it's exactly 90, there's no net energy added to the acoustic field. What this also says is that if the phase lies outside of that minus 90 and plus 90, if, for instance, let's just do a quick polar plot here. So if this is theta, what I just said is that if the phase lies between plus 90 or minus 90, or between 90 between 270 and 90 degrees, however you want to think about it, then that product, P1 times Q1 dot, the time average is greater than 0. If you happen to lie in this quadrant here, between 90 and 270, that product is less than 0. What does that mean? Somebody give me a physical interpretation of that. It's damping. That means that actually the flame is pulling energy out of the acoustic field. It's quieting the system down. So this is, so just coming back to this slide here, what this shows you is this source term, unsteady heat release can either add energy to the acoustic field or it can take it away. And which one it is critically dependent on time delays, on phase shifts between pressure and heat release. And so this comes to something which we call Rayleigh's criterion. And Lord Rayleigh was a independently wealthy guy who could do research without funding. So he's very lucky. He did all kinds of really interesting stuff. His name is all over the place. You've probably heard of him. But he did a lot of work on thermoacoustics. And he's the one who observed this phenomenon first, that if the heat release is rising, when the pressure is rising, you're pumping energy into the acoustic field. That's usually called Rayleigh's criterion. And so just to illustrate this is a bunch of, and so when you have a combustion instability, by the way, during a combustion instability, the flame is pumping energy into the acoustic field. And so therefore, combustion instabilities happen when the pressure and heat release satisfy this phase relationship. Combustors are stable, they're quiet, when the pressure and heat release lies between 90 and 270. So, and just to illustrate that, this is some data from Penn State, from Professor Dom Santavica, where they took a combustor, they ran it over all kinds of different operating conditions. It was stable in some cases, it was unstable in others. And what they did was they measured the phase between the pressure and heat release, or they inferred it, because you can't measure heat release, but you can measure chemiluminescence from the flame, and they assumed that chemiluminescence was proportional to heat release. And so that's what's plotted here. Excuse me, theta PQ is the phase between the pressure and heat release. And then here is the measured pressure amplitude. So this is the fluctuating divided by the mean pressure. And notice how you get, the only place you get large pressure oscillations is when that pressure heat release phase is close to 0 degrees. And when it's outside of this 90 degree or plus 90 degree, notice the system's pretty quiet. Okay. Now, this doesn't tell us, this graph here doesn't tell us what controls the phase between pressure and heat release, which is a whole nother subject. We're going to not have, when we talk about flame response later, we'll get into that a little bit. But what this does tells you is that the pressure and heat release, there's going to be some phase relationship between when the pressure, the acoustic pressure is going up and down and the resultant heat release fluctuations. And if that phase lies between minus and plus 90, you have the potential to have large amplitude oscillations because you're going to be pumping energy into the acoustic field. Again, what this Rayleigh's criterion doesn't tell us is what is that phase? What is the phase between the pressure and heat release? That's a great question. This is what I spend my life doing. This is how I'm going to send my children to college, is trying to understand what controls the phase between the pressure and the heat release. All right, it's a really complicated problem. You're basically trying to understand, basically, if you think about controls class and you have transfer functions, what's the transfer function of a flame? What's the input-output? What's the complex gain phase relationship between the input disturbances and the output heat release response? So, you know, oftentimes when we want to analyze things, we'll say, assume steady state. And we turn off the unsteady terms so we can make analytical progress. You can't do that for this problem to understand it. Okay, so that's all I'm going to say about disturbance energy. What I'm going to do next is I'm going to skip over lots of stuff. And jump straight to unsteady heat release effects and thermoacoustic instability. Okay? So we have a half hour to talk about this. And I'm going to move ahead to this slide. So slide 174. And what I want to do is I want to work through a model problem to derive the conditions under which a combustor would be stable and unstable. All right? And now I just skipped over a whole lot of stuff. So how many of you have had an acoustics class before? Okay, so those of you who've had acoustics will know what I'm talking about. If you haven't, don't worry about it. I'm going to focus my discussion here on when you do and don't get instability. Some of the solutions of the wave equation you'll just have to take my word for. But what I want to look at, this is a problem formulated by Keith McManus. He wrote a really nice review article about 15 years ago. And to illustrate some ideas, assume that I have a combustor. I have a rigid wall here. I have an open piece of pipe here. I have a flame that divides the combustor into two regions, what I'll call region 1 and region 2. And what I want to do is I want to solve for the natural acoustic frequencies. Now I just skipped the analysis of natural frequencies, so we don't have, so again, I'll just summarize a few things. But without the flame, these boundary conditions will support natural mode. Just like organ pipes have natural frequencies, you blow air through it, you excite that natural frequency. Combustion chambers have natural acoustic frequencies. And this geometry will have some natural frequency. And so what we can do in this analysis is we can solve for what that natural frequency is, and we can also determine whether the amplitude of those oscillations will grow or decay in time. And so with this problem, what we do is we assume that we have some reactant temperature which is uniform upstream, some reactant temperature which is uniform downstream. And so although the acoustic field in general in a combustion chamber is quite complex, I can take that fact to write a relatively simple form for the pressure and the heat release in region 1 and 2. And basically what these solutions describe, in words, what these solutions describe are two plane waves. A sound wave, this describes here a sound wave moving to the right at the speed of sound with an amplitude of A1. This term right here describes a sound wave moving to the left with an amplitude of B1. Both of them are moving at the speed of sound. You add the two up, you multiply by e to the minus I omega t, and that's what the space-time dependence of the field is. I don't know what A1 or B1 are yet. I got to figure what those out for my boundary conditions. I also don't know what omega is. That's going to turn out to be the eigenvalue. This is an eigenvalue problem. There'll be discrete values of omega where you can satisfy your boundary conditions. Now this is the corresponding, this is what the pressure looks like. This is what the velocity looks like. So you have plane waves moving to the right, plane waves moving to the left. They superpose with each other to give you the velocity field. In the same way, I can write a solution for the pressure and the velocity in region 2. Potentially a different temperature, well, definitely a different temperature. And I have a plane wave moving to the right with amplitude A2, an amplitude moving to the left with an amplitude of B2. At any given point, what I'm measuring is the superposition of these two sound waves, these two one-dimensional sound waves, and that gives me my pressure and my velocity. So I don't know the amplitudes of these coefficients. I don't know the amplitudes of these waves, A and B, and I also don't know the frequency. So in order to do that, what I have to do is I have to apply these boundary conditions. So I'm assuming that there's no velocity disturbance here. And a pretty good acoustic boundary condition is if you have an open piece of pipe, it looks like what's called a pressure release boundary condition, or a no unsteady pressure boundary condition. So if you've taken gas dynamics and you've looked at shock wave reflections from open-ended pipes, you probably assume something similar, that the reason a shock reflects from an open-ended pipe is because the pressure stays constant. So a shock wave hits an open pipe, excites a expansion wave, which propagates back. In the same way, sound wave hits an open end, it's reflected back out of phase with itself. All right. So anyway, we have these matching conditions here, and boundary conditions here. So for example, we can say at x equals 0, the unsteady velocity is 0. So we can take this equation here to solve for the relative values of A and B. What we can also do is we can do matching conditions or jump conditions across the flame. And we can say for a given fluctuation in heat release, the velocity and the pressure at this interface and at this interface are going to have some relationship. And I didn't have time to do it, but I derived these jump conditions in equations 61 and 62. So here's what happens when you apply those. The left boundary condition gives you this expression. The right boundary condition gives you this expression. And then you do pressure matching across the flame and then velocity matching across the flame. And so these allow you to solve for these coefficients. Now, this is a linear eigenvalue problem, and the one last thing that I need to do to solve it is I need to know what the unsteady heat release is. Now, this is a capital Q. Remember the heat release before was a lowercase q. The reason this is a capital Q is, let's see if I should define it. I don't. Lowercase q denotes heat release per unit volume. The capital Q is the total spatially integrated unsteady heat release. I didn't have time to get into it, but it turns out that as long as your sound wave is large relative to the size of the flame, the spatial distribution of heat release doesn't matter. All that matters is the spatially integrated heat release, the time varying but spatially integrated heat release. And so that's what this capital Q dot stands for. So this is a this is a quantity that only oscillates in time, not in space. And so what this equation is showing you in words is that the flame induces a velocity jump across it. Right, so this is the velocity in region 2. Here's the velocity in region 1. If there was no unsteady heat release, they'd be equal. Because of the unsteady heat release, again, the flame is a dilatation source. It causes a jump in velocity across it. So in order to finish this problem out, we have to have some model for what the unsteady heat release is as a function of my other acoustic variables. And I'll just say so I need an unsteady heat release model. And I'll just say in passing that this is the most challenging part of the combustion instability problem, is predicting this input-output heat release response. I mentioned this before. I said you got to know that transfer function, the complex gain in phase. So I'm going to use what I'm going to call a velocity-coupled flame response. So I'm going to assume that the unsteady heat release at any given time instant is proportional to the unsteady flow velocity just upstream of the flame, multiplied by a gain factor, which is called in. And for historical reasons, we call it in. This is called the in-tau model, by the way. But it doesn't happen instantaneously, that there's a certain time delay between when the flow disturbance hits the flame and when the heat release actually responds. And that time delay shows up here. So the unsteady heat release at each instant in time is equal to the velocity shifted in time at time t minus tau. All right. So you might wonder, well, what's tau physically correspond to? I'll give you a quick example. And we'll dig into this a little bit more in our last session. But here's my flame holder. Here's my flame. Sound wave hits the flame holder. Well, it's going to excite a vortex. And that vortex is then going to convect along the flame. It's going to convect along, and it's going to create local heat release disturbances. And when you add them all up, the heat release fluctuation here is going to be time shifted from here. But overall, if this flame has some length LF, kind of a first cut approximation for that time delay would be 1/2, well, would be LF over 2. Excuse me. Well, I'll just say 1/2 LF over U naught. So basically the amount of time that it takes for that vortex to convect halfway along the flame. This would be a pretty good model, actually, for what that time delay might look like for a vortically excited flame. So that's where the time delay comes from. The bottom line is there's this, and this time delay is critical because time delays are equivalent to phase shifts, right? It just depends on how you want to think about them. A phase shift, omega times the time delay, frequency times time delay is equal to phase shift. So phase, and remember, it's that phase between pressure and heat release which is controlling when I do and don't have an instability. So this time delay is absolutely critical. And as we'll show you, the conditions under which the system's quiet or noisy is going to depend on this time delay. All right, so if you jump ahead, so you take these equations, you now write the unsteady heat release as a function of velocity. You solve all these equations simultaneously. You end up with what's called a characteristic equation. Okay? So for those of you who've done vibrations problems, you'll probably have seen these before. You end up with a characteristic equation, which is an equation for the eigenvalue. So in other words, there exist non-trivial solutions for the dynamics of the system, even when you have homogeneous boundary conditions. Even though this is 0 and that's 0, you can still get interesting non-zero solutions inside the domain, which is unique to vibration problems, right? If you were solving a heat conduction problem, if the boundary is 0, if everything's 0 at the boundary, everything in the domain is 0, right? It's boring. Acoustic problems, you can have everything 0 at the boundary, but you can still have large amplitude vibrations in the middle, right? If you're banging on drums, you can take a membrane, and the amplitude of the membrane fluctuation all the way around the edge of the drum can be 0. That's your boundary condition, but the thing can still vibrate and make noise. So that's what happens. But it vibrates only at certain specific frequencies. Those are the eigenvalues. And it oscillates with certain prescribed shapes, which we call the eigenmodes. So this is a characteristic equation for that eigenvalue, that natural frequency. All right, and you can see it's a function of the density jump across the flame, ρ2 over ρ1. It's a function of the speed of sound jump across the flame. You can put both of these in terms of the temperature change. It's a function of, in that gain factor. It's a function of tau and other stuff. So you can solve this thing computationally and get an answer out. But I want to build some insight, so I want to solve this thing analytically. So I'm going to make some fantastic assumptions. In particular, I'm going to assume that the temperature jump across the flame I can neglect. So I'm going to have an isothermal flame. And again, this isn't reality, but if this thing isn't 1, I can't solve it analytically. So we're going to neglect the temperature jump because I really want to focus on the effect of this term right here. This term right here is giving me unsteady heat release. And I want to talk about how that will cause oscillations to grow or decay. Okay, so it turns out that even in that case, you can't actually, so this becomes your characteristic equation, the new characteristic equation, where K, I didn't define K before, but K is equal to omega over C. K is your wave number. And now there's only one C, so I don't need to differentiate between C and C naught. So cosine KL equals n times e to the I omega tau sine squared KL over 2. And so there are unique values of omega, or K, whichever one I want to solve for, which satisfy this equation. All right, this is still a transcendental equation. You can't solve it. So what I'm going to do is I'm going to make one more approximation. I'm going to assume that n is really, really, really small. So I have a flame. The heat release is oscillating, but it's just oscillating a little bit. And so what I can then do is I can expand this. I can solve for the solution where this whole thing is 0, which would be the solution with no unsteady heat release, and then I can do a Taylor series expansion around that solution. And so that's what I've done here. So we expand the solution around its n equals 0 value, and then we'll look at a Taylor series in the limit of small gain. And so this is what it looks like. So the wave number k is equal to its value when n equals 0 times 1 minus a quantity which is directly proportional to n plus higher order corrections, which are of order n squared and n cubed. We're going to neglect those. We're only going to look at the leading order term. And the value of k when n is equal to 0, it turns out that that's this right here. This corresponds to what we call a quarter wave mode. This is the quarter wave mode of that duct. It's an organ pipe mode. All right? Okay. Does anyone have a question? I want to make sure that I'm going into sufficient detail that you're somewhat following me, but not too much detail so that we have 20 minutes to be done with what I want to say. Okay. All right. So now something you may not be super familiar with, and that is notice that k, that this correction, n multiplies e to the I omega tau, and this is a complex number. So what this means is that your frequency or your wave number is complex. And you might not be used to thinking about what does a complex frequency mean. So I want to explain what that is. So since the wave number and frequency have an imaginary component, in order to understand that, if you take omega, if you take a quantity that oscillates as e to the I omega t, or a harmonically varying quantity, e to the minus I omega real plus I times omega imaginary times t. And you expand it, you get what I have over there. And what that tells you is that the real part of the frequency is the actual frequency that we're used to thinking about. It's the harmonically oscillating part. But the imaginary part denotes a exponentially growing or decaying harmonically oscillating disturbance. And now, if you're not comfortable working with complex notation, I mean, I could have done this thing with cosines and sines and exponentials and not done anything, but it would have been 10 times as much work. And it just turns out that when you do the math in using complex notation, a complex frequency physically corresponds to an exponentially growing or decaying disturbance. So what this means is that what I really want to figure out is what's omega imaginary. Because omega imaginary, if it's positive, that means I have harmonic oscillations, but they're exponentially growing in time. I have an instability, is what that means. If omega imaginary is negative, harmonic oscillations decaying exponentially in time, and the system's stable. And now remember that this complex part, the complex part of the wave number, the frequency, is multiplied by n. So when that unsteady heat release is 0, the frequency is purely real. So oscillations, so since this problem didn't include any damping processes, the oscillations just persist without any, with constant amplitude. As soon as I add unsteady heat release, the oscillations can grow or decay in time. So what I can do now is I can write this out, and I can write out the part for the real part of the wave number and the frequency and the imaginary part of the wave number and frequency. So here's what the real part looks like, and here's the formula, and here's what the imaginary part looks like, and here's the formula for the imaginary part. And this is what I want to really focus on, because what I'm interested in is under what conditions is this thing positive. And you can see what it happens is n happens to correspond to which mode. There's a quarter wave mode, or that's the fundamental mode. N equals 1 would be the fundamental mode. N equals 2 would be its first harmonic. N equals 3 would be the third natural mode. So in other words, quarter wave, 3/4 wave, 5/4 wave modes, higher order modes. Don't worry about that for now. Bottom line, though, is that the growth or decay rate is proportional to this thing. And you can see it's this sine omega tau. So sine omega tau can be positive or it can be negative. So the oscillations can grow in time or they can decay in time. So let's jump ahead a slide. So if we look at the n equals 1 mode, which is my quarter wave mode of this duct, is that mode going to be stable or will it be unstable? And what I've done here is just focus attention here on this bottom plot. This x-axis corresponds to, what I'm doing is I'm plotting omega times tau. But rather than plotting it as omega, which is the angular frequency, I'm normalizing. So notice omega times tau, I can also write that as omega is 2 pi f, right? 2 pi times the frequency. This is angular frequency. This is frequency in hertz. F times tau. The frequency is 1 over the period. So this is equal to 2 pi tau over the period. But I use that fancy script t there. And the subscript 1/4 means the period of the quarter wave mode. And so what I'm doing is I'm just plotting the ratio of the time delay between the velocity and heat release disturbance to the acoustic period. All right, so sine omega tau. And what this shows you then is that when tau over t lies between 0 and 1/2, so let's come over to here, this equation here. So when tau over t lies between 0 and 1/2, this quantity is positive, that thing's negative, therefore this is a stable negative number, positive number, so omega imaginary is negative, stable configuration. However, when tau over t moves past 1/2, or in other words, when omega times tau is bigger than 180 degrees, I become unstable. So what this shows me then is that you get these oscillating bands of stable and unstable, stable and unstable for these different modes, depending upon what the period of oscillations are, or what the frequency, or what the time delay, or what the period of oscillations are. Now, we're not going to worry about the 3 higher order modes or frequency shifts. Just focus attention here. But again, what this tells you is that the significance of this time delay, that the time shift or the phase delay between when you disturb the flame and when it responds critically controls when you get heat release oscillations. And so now let's just think about a simple thought experiment. Let's suppose I have a bluff body stabilized flame in a duct. It looks like that. And I already told you a reasonably good model for tau is that it's 1/2 flame length divided by flow velocity, right? Flame length. Not flame thickness, but flame length. Because if it's a vortically driven, I said an acoustic wave excites a vortex. It takes it a certain amount of time to convect along. When you add everything up, this is a pretty good model. So imagine that I change my fuel-air ratio, and I make it leaner, so I decrease the flame speed. What's going to happen? The flame's going to do this. It's going to get longer. I just changed tau. So if you're having trouble thinking about physically what's happening to move along that x-axis, think anything that changes how long the flame is moving me axially back and forth on that plot. And so if I happen to sit here, let's suppose that I start my combustor up, I'm right here, it's real quiet, and then I decrease the equivalence ratio, I make my flame longer, like I've shown over there. At some point I'm going to move across a boundary and all of a sudden it'll be like somebody turned on a function generator. This thing is going to just sing at a tone. I mean, it's so narrow band. And I mean, if any of you have done an experiment with a combustion instability, you'll know what I'm talking about. You just change something, all of a sudden, beep, it's really, really tonal, or it could be much louder. It could blow your ear out. But what's interesting about this is that notice that right smack in the middle of this thing, that's where the pressure and heat release are exactly in phase. So this is where Rayleigh's criterion is satisfied. When you lie within here, the pressure and the heat release phase is minus 90. Here it's plus 90. Here it's 0. We can imagine that there's going to be the biggest amplitude oscillations right smack there because they'll be exactly in phase. The flame will be pumping the most energy into the acoustic field. So think about what's going to happen here. I'm increasing my flame length. I'm decreasing fuel-air ratio, let's say. Flame instability amplitude is going to grow. It's going to grow. It's going to grow. I do this. Then what happens? It decreases, right? And then at some point, I pass this boundary, and all of a sudden, the sound, as mysteriously as it came, has disappeared. And then I keep merrily decreasing my fuel-air ratio. So, and then what happens? All of a sudden, there it comes again. So you get these islands of instability. And this goes to the fact that this is a periodic phenomenon, right? So if that's my pressure, and this is my heat release, there's some shift between the two. So as I'm changing the flame length, what I'm doing is I'm basically shifting the one curve relative to the other. But because it's harmonic, once I shift it past a certain amount, I'm back where I started. I've shifted it all the way back to 360 degrees. The instability comes back. If I keep going, it'll become quiet again, but then I'll be at 720 degrees. So this is one of the key things that makes combustion instability such a pain in the neck, because you get, what this shows you is there's this non-monotonic variation of instabilities, amplitudes with your underlying conditions. All right? So let me, just to help you appreciate that, let's think about some of the other things that we've talked about in this class. Let's just say NOx emissions. All right? So you all graduate, you get a PhD, you go get a job working for somebody, and your boss says, hey, I'm thinking about making this change to the system. We'd like to maybe turn down the flame temperature by 10 degrees. Can you just give me a quick estimate of what that's going to do to NOx? And you can all say, well, I'll probably have to turn the computer on to give you a quantitative number, but I can tell you that NOx will go down, right? If you make the temperature colder, probably NOx is going to go down. You all have a great directional barometer, right? Or you could say, if he said, I'd like to, a customer called us and they want to take our lean premix system, and they want to know what happens if I, instead of burning natural gas, it has 50% hydrogen in it. What do you think? You think there's a problem with that? And you'd say, well, yeah, we might have a flashback problem. I don't exactly know where the flashback is going to occur, but I know that hydrogen really propagates fast, and so it's going to decrease the operability window where I can have flashback. So again, you didn't need to pull out the computer. You have a directional barometer. Or blowout, right? You could say, well, we got this system and we designed it, and then somebody at the San Diego County landfill wants to use it to burn their landfill gas. What do you think? And you could say, well, landfill gas, it's got a lot of carbon dioxide in it. Going to decrease my flammability range. My combustor will blow off easier. So I don't exactly know what fuel-air ratio it'll blow off, but I can tell you that if natural gas blows off at an equivalence ratio of 0.7, it's going to blow off at something above 0.7. Combustion instabilities, you can't do that. So, again, your boss comes to you and says, hey, and by the way, what's it going to do to combustion instabilities? It's non-monotonic, right? You could say, well, it's going to make the amplitude go up, or it could make it go down, or it could have no effect at all. Right? So that's not very appealing. But this is why this problem is so hard, is because it's this non-monotonic dependence. And so things like NOx, CO, flashback, blow-off, blah, 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 you can make definitive statements about whether a given delta or change will have a good or bad effect. The same change on two different systems in the combustion stabilities could give you two different answers. I'll give you an example of that. A colleague of mine worked for a company that made low NOx burners for gypsum drawing, for basically making what do you call this stuff on the wall? Drywall. And so they made this burner. It worked great, and they put it in some. And so in fact they tested it at a customer site. The thing worked perfect, no problem. It was real quiet. Then they sold it to some other customers, and so let's just assume that happened to that system was quiet, and let's just say that system was sitting right there, okay? Let me just draw you a picture here, just so we're all on the same page about what I'm drawing here. So here's some big furnace, and here's my burner, my low NOx burner, etc. It worked great. All right. Then they sold it to someone else, and they said, well, actually our configuration looks a little different. It turns out that our combustor's twice as big. What do you think might happen? Same fuel, same operating conditions. You'd say, you know, my burner, I've got it mapped out. I know where my operability window is. But what do you think you might have to worry about? Pardon? Natural frequency, right? This system, I just told you that. So if it's twice as big, round numbers, what's going to happen to the natural frequency? It's going to be half, right? Okay, so now if our flame doesn't change at all, let's just assume that everything about the burner stayed exactly the same. Tau didn't change. I just doubled T. I said, let's start here. Now all of a sudden, I'm here. Tau over T half. This thing just vibrates like crazy, all right? And this is why making low NOx burners is such a pain in the butt, is because it's intrinsically, combustion stability boundaries are not intrinsic to the flame itself. They're completely a system problem. The same burner can have totally different behavior depending upon the natural frequency of the system that it's in. So this drives people crazy because you want to just develop a single product and then just market it for all kinds of different applications, and the thing will act totally different because the different applications have different natural frequencies. And this stuff happens all the time. And now just to show you that I'm not making this stuff up, I have a whole bunch of different data sets in here, and I'm just going to go through them fairly quickly. This is just to illustrate a couple ideas. This is a really neat combustor that Professor Dom Santavica from Penn State built, and it really nicely demonstrates some of the points I was making. And so what he did was, in general, when you do a test like this, let's just say you go over here, you build it, and it's quiet, and you say, whew, I know it's okay. The problem is, if you think about that little tau over T map I drew, you don't really know where you are on that map. And so you don't really know how things are going to change as you start changing the period. So what Professor Santavica did, he built a variable length combustor so he could sort of keep a fixed flame, and he could change that T. He could vary that tau over T. So that's the x-axis. Excuse me, the y-axis. That's combustor length. And then the x-axis is he just happened to vary fuel-air ratio. And so I'm speculating here, but my guess here is that by increasing the fuel-air ratio, you're increasing the flame speed, which is making the flame shorter. And by making the flame shorter, you're decreasing your time delays. So decreasing time delay, decreasing period. And then these are isocontours of pressure amplitudes. So let's suppose you have a given combustor length, 50 inches long. What you can see is you start here, you have, what would that be? 4 psi oscillations. Then as you increase, the equivalence ratio goes 4 to 3 to 2 to 1 psi. Now, if you happen to start, on the other hand, with a 40-inch combustor, identical flame, 1 psi, then 2, then 3, then 4, reaches a peak, then back down 4, 3, 2, 1. So it just shows you this non-monotonic variation. Again, this is the real challenge that we have with this instability problem. Okay, and then I have some other data from other people. Again, you can see this non-monotonic variation. You can see the ups and the downs as you change things, but it's the same basic idea. Okay, does anyone have any questions about the crash course in combustion instabilities? So just to summarize again, because it's a time harmonic phenomenon, and because Rayleigh's criterion says what matters is the phase between pressure and heat release, that by varying time delays, you're moving in and out of the pressure in and out of phase with each other, you get this non-monotonic variation, which is something quite unique to the, not completely unique, but it's a real distinctive about the instability problem. Okay, so what we'll do is we'll take a quick break. It's 4:01. We'll reconvene at 4:10, and we'll move into our last topic.